Section 2.2, Solving Linear Systems in Two Variables with Substitution and Elimination. This section will focus on the algebraic techniques for solving systems of equations in two variables. I should say linear systems in two variables. Those methods that we will be discussing is the substitution and elimination methods. We'll also again see how we can classify systems based on the type of solutions they have, and we'll look at a couple of applications. So here's a procedure we can use to solve by substitution. We'll see two equations, and we want to first solve one of the equations for one of the variables in terms of the other. We will then substitute the expression from step 1 into the other equation to get an equation in just one variable. We'll solve for that variable. And then we'll substitute again. We now have one of the variables solved for. We substitute the value found in step 2 into either of the original equations to find the remaining variable. We'll write the solution as an ordered pair and check that solution to the system in both original equations. And of course, when we solve an application problem, we want to state the answer in the context of the problem. So here's our first example. We want to solve using substitution. This system x minus 2y equals 2 and 3x plus y equals negative 14. Using the substitution method, our first step tells us that we want to solve one of the equations for one of the variables. Now, I look at this system and I see two possibilities. It would be very easy to isolate the x in the first equation or the y in the second equation. I'm going to solve for the x in the first equation. So I'm going to isolate that variable. And to do that, all I need to do is add 2y to both sides of that equation. So that would yield then x is equal to 2y plus 2. So now I have one of the variables isolated. So now here comes the first substitution. I'm going to take this 2y plus 2 and use it to replace the x in the other equation, yielding 3 times 2y plus 2 plus y is equal to negative 14. So notice when you make that substitution, you really need to put that in parentheses, because in this case we have to multiply that whole quantity by 3. So then that gives me 6y plus 6 plus y is negative 14. So then 7y plus 6 is equal to negative 14. So then subtracting 6, 7y is negative 20. And then dividing by 7, y is negative 20/7. So now that we have the y value, we need to substitute back and solve for the x value. Well, recall that earlier we said that x was equal to 2y plus 2. So then the x value would equal 2 times the y value, negative 20/7, plus 2. So x would equal negative 40/7. And adding 2, but thinking ahead, I'm going to add 2 in the form of 14/7. 2 is 2 over 1, multiplying by 7 is 14/7, so x is equal to negative 26/7. So my solution then is negative 26/7, comma, negative 20/7. Now we should check our work. I'm going to use a calculator for the check just because we're dealing with some fractions here. Let's see, negative 26 sevenths, negative 20 sevenths. Alright, so using the calculator, if x minus 2y is supposed to equal 2, then negative 26 sevenths minus 2 times negative 20 sevenths is 2. That's good. Now let's check the 3x plus y. 3 times negative 26 sevenths plus negative 20 sevenths. This had better give me negative 14, and it does. So that checks out, and I'm comfortable with my solution. We're asked to solve using substitution. 3x minus y equals 6, and negative 4x plus 2y equals negative 8. So looking at this, I think the easiest variable to isolate is the y in the first equation. It is a minus y, so we have to be a little bit more careful. So let me subtract 3x from both sides. That would give me negative y is equal to negative 3x plus 6, and then I'll divide through by negative 1, yielding y equals 3x minus 6. So I will substitute 3x minus 6 for y in the other equation. So we have negative 4x plus 2, now substituting for y as 3x minus 6 equals negative 8. Applying the distributive property, negative 4x plus 6x minus 12 is negative 8. Combining like terms, 2x minus 12 is negative 8. Adding 12 to both sides, 2x is 4, and dividing by 2, x is equal to 2. We have the value for x. Let's find the value for y. Well, y is 3x minus 6. So then y would equal 3 times 2 minus 6, which is 6 minus 6, which is 0. So then my solution is 2, 0. And we can easily check this one since we have integers. So I'll check this one by hand. 3 times 2 minus 0. Is this equal to 6? Yes. Negative 4 times 2 plus 2 times 0. Is this equal to negative 8? Negative 8 plus 0 is negative 8. So that checks out as well, and I'm confident in my solution, negative 2, 0. The other technique we're going to discuss is called the elimination technique. And to solve by elimination, the first step is to eliminate one of the variables of the system by using the concept of opposites, and specifically adding opposites. When you add opposites, the result is 0. So if necessary, we will multiply one or both equations by non-zero constants that will produce coefficients of either x or y that are opposites of each other. We will then add the two equations, making sure that one of the variables eliminates or drops out, leaving us with one equation and one unknown. We'll solve the resulting equation for the variable. And then we will back substitute the value found in step 3 into one of the original equations to find the value for the remaining variable. Again, we'll write the solution as an ordered pair, check the solution in both of the original equations, and of course when solving an application problem, we'll state the answer in the context of the problem. So here's an example. 3x plus y equals 3, 2x minus 2y equals 10. We're going to use elimination to solve this system, and so the first thing I'm looking for is, I'm thinking opposites. I want to either get opposites on the 3 and the 2, or the 1 and the negative 2. So I'm just sort of thinking ahead, which might be easier, and I'm thinking, I'm going to focus on the y's. I'm going to focus on those coefficients. I have a positive 1 and a negative 2. I want them to be opposites, so all I would need to do is multiply this y by 2, and that would give me a positive 2y, and I'd have the negative 2y to eliminate with. So I multiply the entire first equation by 2. The second equation I'm going to leave alone. So now this gives me 6x plus 2y equals 6. And the second equation is still 2x minus 2y equals 10. Notice I have opposite coefficients on y in this new system. So what I can do now is add these equations together, yielding on the left 8x, 0y, so we don't write that, equals 6 plus 10 is 16. We divide through by 8, and x is 2. So we have the value for x. Now, I'm going to take that value for x and solve for y by substituting back into one of the original equations. I'm just going to use the first equation. So now using 3x plus y equals 3, 3 times 2 plus y equals 3, 6 plus y equals 3, subtracting the 6, y equals negative 3. So, I'm guessing that the solution, not really a guess, but I think the solution is 2, negative 3. All right, let's check in our equations. 3 times 2 plus negative 3, that's 6 plus negative 3, that's 3. Good. In the other equation, 2 times 2 minus 2 times negative 3, is this equal to 10? 4 plus 6 is 10. That checks out as well, so I'm very confident in the solution of the system. Let's see another example using elimination. X over 8 minus y over 2 equals 1, and x over 3 minus y equals 2. Now we could try to use an elimination directly, but it gets a little messy when we have these fractional coefficients. So the first thing I'm going to do is I'm going to multiply to get rid of these denominators. So I'm going to multiply the first equation by its common denominator, which is 8, and the second equation by its common denominator, which is 3. And so that yields then x minus 4y equals 8, and x minus 3y equals 6. And now it's very easy to see what to eliminate on. Notice I have a positive 1x in both equations, so now what I'll do is I'll multiply the second equation by negative 1. I could have just as easily multiplied the first equation by negative 1, yielding x minus 4y equals 8, and negative x plus 3y equals negative 6. Be very careful with your signs. Notice now we have that elimination on x. We'll add together the equations. The x's eliminate. I would have a negative 1y equals 2, and so dividing through by negative 1, y is negative 2. Now I'll go back into one of the original equations. I'll use the first equation. So using x over 8 minus y over 2 equals 1, then x over 8 minus negative 2 over 2 is 1. So x over 8 minus negative 1 is 1. X over 8 plus 1 is 1. X over 8 is 0, and so that implies that x is 0. So the solution is 0, -2. Let's check into each equation. Let's see, 0 over 8 minus -2 over 2 is 0 plus 1, which is 1. That checks out. And the second equation is 0 over 3 minus -2. That's 0 plus 2, which is 2. That checks out as well. So the solution is 0, -2. All right. So this one asks us to solve if possible. We have the system 4x plus y equals 2, and 2y equals -8x plus 4. It doesn't tell us to use a specific method, so we can use whichever one we want. Now, I look at this and I would use an elimination, I would use a substitution, because it's very easy to isolate this y variable. Alright, so then that gives me that y is equal to -4x plus 2. So now I'll make my substitution. I'm going to take that -4x plus 2 and substitute into y in the other equation. So I'd have 2 times, substituting for y, -4x plus 2 equals -8x plus 4. Alright, simplifying on the left-hand side by using the distributive property, I have -8x plus 4 is on the right-hand side -8x plus 4. Now look, you see how both sides are exactly the same? This is called an identity. When something like this happens, when we're solving a system of equations, this tells us that we have a consistent and dependent system. Alright, so when this happens, the system is consistent and dependent. Alright, so what that tells us is the system has infinitely many solutions. Alright, so again, if you're solving the system and you use one of those, one of the symbolic techniques, and we end up with an identity, the system is consistent and dependent, and the system will have infinitely many solutions. Solve if possible. 4y minus 7x equals 18, and 2y plus 15 equals 3.5x. Alright, it doesn't give us a specific method. I don't see an easy variable to isolate, so I'm going to use elimination, but before I use elimination, I'm going to put this in a better form. I'm going to move these two terms to the other sides, so the second equation looks more like the first. Alright, so the first equation, 4y minus 7x is 18. The second equation would then be 2y minus 3.5x equals -15. I just moved each of those to the other side. Alright, so now I'm going to do an elimination, I think. I'm going to focus on the 4y and the 2y. I'm going to multiply the second equation by -2. That would give me a positive 4y and a negative 4y. So that will give me 4y minus 7x equals 18. I still haven't changed the first equation. And I'll have a negative 4y. Now let's see, -2 times -3.5, that would be a plus 7x. And -2 times -15 is 30. Now notice what happens here. We get the elimination on y. That was our goal. But notice we also get an elimination on x. So when we add these equations together, the left-hand side becomes 0, and the right-hand side is 48. Is 0 equal to 48? Never. So this is called a contradiction. And when we're solving a system of equations and we get a contradiction, what that tells us is the system is inconsistent and independent. And so our conclusion is the system has no solution. All right, so we'll finish off the section with a couple of applications. The first, Maria went to the store and bought a total of 45 calculators. She paid $9 for scientific calculators and $58 for used graphing calculators. Maria spent a total of $1,728. Let's use S for scientific and G for graphing calculators to find how many of each she purchased. All right, so what about the scientific and graphing calculators? Well, I'm going to let S represent the number of scientific purchased. Similarly, I will let C represent the number G. Let G represent the number of graphing purchased. All right. So now what we're going to do is I'm going to try and set up a system of equations that I can use to solve this problem. All right. Bought a total of 45 calculators. Well, as far as we know, there's only two different types of calculators that she bought, scientific and graphing. We don't know the specific numbers, but we know the total is 45, so then the number of scientific plus the number of graphing must have been 45. She paid $9 for scientific and $58 for used graphing calculators, and she spent a total of $1,728. So she bought S scientific calculators at $9 a piece. So then the total amount she spent on the scientific calculators would be 9 times S. Similarly, she spent 58 times G for the graphing calculators, and the total amount of money spent is $1,728. So now we have a system of equations in S and G that we can use to solve this problem. We can use an elimination or a substitution. It doesn't really matter. I'm going to use a substitution. I'm going to solve the first equation for S. So then S is equal to negative G plus 45. And I'll make that substitution, negative G plus 45 for S in the other equation, yielding 9 times negative G plus 45 plus 58G is 1,728. So then negative 9G plus 405, let me double check that number, 9 times 45 is 405, okay, plus 58G is 1,728. So let's see, negative 9G plus 58G, that's 49G plus 405 is 1,728. 1,728, let me subtract the 405, is 1,323. So 49g is 1,323. And I'll divide through by 49, and g is 27. G is 27, and S is equal to the negative G, so negative, and substituting 27, add 45, S would equal 18. Alright, so let's just run a quick check. 18 and 27 does add up to 45. Let me use the calculator for the other. Let's see, 9 times the number of scientifics was 18, plus 58 times the number of graphing, which was 27, is 1,728. That's good. So my conclusion, Maria bought 18 scientific and 27 graphing calculators. All right, another application. Josephine wishes to mix candy worth $1.80 per pound with candy worth $2.40 per pound to form 48 pounds of a mixture worth $2 per pound. How many pounds of the more expensive candy should she use? We'll use X for, we'll use X for the pounds of cheaper candy. And we'll use Y for the pounds of more expensive candy. Alright, so let's see. The cheaper candy is $1.80 per pound, and the more expensive candy is $2.40 per pound. She needs to make 48 pounds of a mixture. Alright, so we're mixing these two together. Well, we have X pounds and Y pounds that we're mixing together, so I know that X plus Y must be 48. So that takes care of sort of the pounds, the weight. Now let's look at the value. What was the value of the cheaper candy? Well, we have X pounds at $1.80 per pound, so the value of the cheaper candy is $1.80 times X. Similarly, the value of the more expensive candy is $2.40 times Y. So if we add those values together, that must be equal to the value of the mixture. Now the mixture is worth $2 a pound, and how much does the mixture weigh? Well, we'd have $2 a pound by 48 pounds. So here's the system that we can use. And let me just simplify on the second equation. We would have X plus Y equals 48, and 1.8X plus 2.4Y, and 2 times 48 is 96. Again, I'm going to use a substitution here because that's the easiest method that I see. Since I have X plus Y equals 48, I'm going to write that X equals negative Y plus 48. And so that's what I will substitute in the other equation. Alright, so 1.8 times negative Y plus 48 plus 2.4Y is 96. So negative 1.8Y, using the distributive property here, 1.8 times 48 is 86.4. So plus 86.4 plus 2.4y is 96. Negative 1.8y plus 2.4y is 0.6y. Plus 86.4 is 96. Subtracting the 86.4 from both sides gives me 9.6, so 0.6y is 9.6, and dividing the 9.6 by 0.6 gives 16. So y equals 16, and x would equal the opposite of 16 plus 48, so x would equal 32. So it looks like we've got 32 pounds of the cheaper candy and 16 pounds of the more expensive candy. Now, one kind of quick way to think about this is notice the individual prices were $1.80 and $2.40, and that the mixture was worth $2 per pound. Now, since $2 is closer to $1.80 than $2.40, that means we should have more of the cheaper candy. Right, if we just sort of think about how weighted averages work. All right, and we do have more pounds of the cheaper candy. The two values certainly add up to 48 pounds. Let's do a quick check of the value. $1.80 times 32 pounds plus $2.40 by 16 pounds is $96. So the value of the mixture was $96, and that's what we had earlier. And so I'm confident in my solution. And so I'll write the conclusion that Josephine needs to mix 32, well, what are we asked for? It says we specifically want how many pounds of the more expensive candy should she use. So Josephine needs to use 16 pounds of the more expensive candy. All right, that concludes the presentation for section 2.2.